So the next talk is on occlusion-aware hand pose estimation using hierarchical mixture density network. The work is done by Jie and Tae-Kyun Kim from Imperial College London.
Good afternoon, everyone. The work I'm going to present today is occlusion-aware hand pose estimation using hierarchical mixture density network. 3D hand pose estimation has gained increasing interest in recent years with with the commercial depth cameras. We can see many companies have incorporated or are planning to incorporate hand interaction into their product. The problem can be formulated as configuring the pose parameters representing a hand model, given a depth image. The parameters can be 3D joint locations or the angles between the bones. For this formulation, we can learn a mapping function between the input image X and its label Y if a label dataset is given. Prior methods choose decision forest, 2D CNN or 3D CNN as the function. They has proven to be very effective in most cases. However, they are not able to handle occlusion very well. So what's the problem under occlusion? Here we have some example images from the big hand dataset, which is released in 2017. The blue skeleton are the ground truths for the visible joints, and the skeletons in other colors are for occluded joints. So for these cases, if we use the mapping function, the function needs to learn input X to multiple pose configurations. So what will happen? For example, if we use the CNN trained with a mean squared error. Okay, for this image, the red skeleton is a prediction from the CNN trained with a mean squared error. We can see for the visible joint, the prediction is quite close to the ground truth, while for the occluded joints, it is not close to any. So to clarify this problem, suppose we have a data set consists only 2 images, as in A, and its label is shown in the yellow skeleton in D. So if we use this data set to train the CNN, and after convergence, the CNN will produce an average of these 2 labels for the occluded joints. So apparently, this average is not a correct solution for articulated objects. So how do we solve this problem? We propose to solve this problem by a two-level hierarchy. In the top level, we have a visibility variable representing a joint is visible or not. So if, and in the bottom level, we have the joint locations are modeled by, are modeled depending on the visibility. So when V, the joint is visible, and V is 1, the joint is actually deterministic, but considering the label noise, we can see we can cheat the Y, the location Y is drawn from a single Gaussian distribution. And when V is 0, the joint is occluded. And all the possible locations for this joint can be modeled by a Gaussian mixture model. So the distribution of location Y, depending on the visibility V, is like this. And the joint distribution is given like this. So after the density function for this pose space is defined, our problem is how to set these parameters. Note that this density function is dependent on the input X. So we can see the parameters of the density function is kind of is also dependent on X. We can see it as a function of the X. And the density function is differentiable. We can choose to learn F by CNN. The output of the CNN parameter is a parameter for the loss or for the density function. So given a data set consists of triplet of X, input image X, all the possible locations Y, and its visibility, the likelihood over the data set is the product of all the individual images and its joints. So now our goal is to learn a neural network that produces parameters, maximizing the likelihood on a data set. And we use the negative logarithm likelihood as the loss function. It will result in 3 terms. The first term is used to train W. It is the probability of a joint being visible. And the second term is to train the mean and the standard deviation of the single Gaussian model for the visible joints. So the final last term is to train the parameters for the multi-Gaussian model. It is to model the occluded joints. So till now, we have the architecture and the loss. We can just feed it with data for training. So to evaluate our methods, we investigate some 4 data sets and choose the egocentric subset of the big hand data set, as it has many occluded joints. In this figure, the first figure is the rate of the occluded finger joints for each data set. So here we show estimated distribution of HMDN. One sphere represents a Gaussian component. The mean is the mean of Gaussian, and the radius is the standard deviation of the Gaussian component. We construct 2 variants. SGN models both the visible and occluded joint locations using a single Gaussian component, while MDN using multiple Gaussian components. And then we draw 100 samples for each fingertip. So for the visible joints, samples from SGN and HMDN is compact and is near the ground truth. While the samples from MDN, we can see in the middle, it is scattered in a larger region compared to the other samples. And for the occluded joints, samples of SGN spans in a very large region. You can see the samples for different tips are heavily overlapped with each other. And the samples from MDN and HMDN actually form an arc shape, which align with the movement range of the fingertip. So as we can see from these sample images, we can see the HMDN combines the advantages of SGN and MDN. And to compare the variance, we draw one hypothesis is drawn from these distributions and is compared with the post label. So the number 10, 20, 30 represent the number of Gaussian components for MDN and HMDN. Each group is, for example, for the first group, and we can see both visible and occluded joints. The HMDN produce lower error. And we can see also, like, with the different number of Gaussian components, the error of HMDN doesn't change quite much. So as there are many post labels for the occluded joints, we also measure the alignment of the samples from estimated distribution and the ground truth. The measurement is the distance between the set of samples drawn from distribution and the set of the ground truth label. And the error, and we can see the error of HMDN is lower than that of SGN, and have a similar error of MDN. So when compared with prior work, we choose MSSD as it has considerable number of occluded joints, both in training and the testing set. We compare HMDN with 3 methods. The first figure shows the comparison use the common used measurement, the proportion of joints with different error threshold. And we can see our method improved quite a lot compared with other methods. Also, we further compare the samples drawn from this method. For these two methods, the green and the blue one, they are able to produce multiple samples, and we compare these samples from 3 methods. And compared to these 2 words, HMDN has low variance. We can see as the numbers of the sample increase, the error from 1 to 100, the drop is very small for our method, and we can achieve a lower mean error at the end. So HMDN can be easily embedded into other methods. The distribution can be used to generate hypotheses, or just we can just use it as a loss term for a model-based method. Also, the product of the distribution from different viewpoints will have a peak response near ground truth. The first speaker and the third speaker, for example, in their application, like for this viewpoint, you may have a Gaussian like this, and for this viewpoint, you may have a Gaussian distribution like this, and the intersect will give a high response. So also we can use the motion information in the video, and incorporate constraints from objects when hand interact with objects. We use this motion information and constraint from objects and combined with this distribution, we can finally fix the occluded joint locations. So for the takeaway of the message, our methods find out, we first propose the problem. Occlusion hand joint has multiple plausible poses, and the conditional average produced by CN trained with MSE is not necessarily a kinematic plausible estimation. And we propose HMDN to model this multimodality of the output space depending on the joint visibility. And here we have a demo. A demo video show the estimated, especially this part, for the occluded joints. And thank you. Welcome to our poster for the questions. Thank you.
Are there any questions? So if not, let's start me with one question. How many annotations do you have of occluded joints in your data set? So how reliable are the annotations of the occluded joints?
Yeah, for the joints, actually, we didn't manipulate the data set because this is a subset of the big hand data set. When we list mostly egocentric, and when we collect the data, the sensors are attached to the fingers. And so for image for in occluded case, for example, if we do poses like this, and it's actually capture all the movement under this occlusion. So for the data set, we have many cases like this. So we actually don't know how many post labels for the distribution, but actually. In order to model this distribution, you need to have enough. And as considering how much is enough, we haven't conducted this experiment. And so in the experiment, we choose a different number of Gaussian components to see whether the distribution, also the number of components, will affect this distribution. The effect. And we see using different number of Gaussian components won't affect this distribution modeled. But we don't know how many labels will affect the final estimation. Yeah. Thank you.
Any other question? Maybe just like a last question. I mean, at the moment you have the handling of the occlusion just for a single hand. So do you also plan to have the occlusion when you have interacting with objects? Is it also like a plan, or you also want to address this issue?
Yeah, you see whether this model can be like extended into the hand objects.
Yeah.
Yeah, that's what I want to extend this work to, because the output is a Gaussian, and if we have some other constraints, it's like this estimation can be a prior, or the constraint maybe another prior. You can just multiply this distribution, and this will give, I think, it will resolve this occlusion issue.
Okay, so let's thank the speaker.
Thank you.